So before we complete this chapter on Sylow theorems, we'll do some more problems. So, and before coming to the first problem, I want to establish one more result which does not directly use Sylow theorems, but we'll be using this result for doing the problems. So the result is this. Let h and k be two finite subgroups of a group G. Then the order of hk is equal to order of h times order of k divided by order of h intersection k. This is a very simple result. This, by the way, does not need to be a group. This is what I mean by this one is it's a number of elements in hk. hk is defined as hk where h belongs to h and k belongs to k. Does not need to be a group always. So this is a very simple result, but we are going to use this, so I thought we'll prove this one. So let h is equal to r and or k is equal to s and the order of h intersection k is equal to t. So hk will have at most r as elements, right, with this definition. But some of them are repeating, maybe, sometimes. So for each x in x intersection k, we can write hk as hx times x inverse k. That is because this x belongs to h, so this is in h and this is in k, because x belongs to this, and this could be h itself. In that case, x is e. But for each x in x intersection k, you can write any element here like this. So that implies every element or an element in hk will be repeated as many times as there are elements in h intersection k, and that implies hk elements, the order of hk is equal to order of h times order of k divided by h intersection k. Our next problem is to find out the conjugate classes of the dihedral group. So find conjugate classes of D4, and also you can find the class equation. Okay, we have done the orbits of a D4 set earlier. This is our table for D4. Sigma 1, sigma 2, sigma 3 and sigma 4 are rotations. Mu1, mu2 are horizontal and vertical images, and delta 1 and delta 2 are diagonal images. So this is the binary operation table for D4. What we had done earlier was that our D4 set was the vertices of a square, midpoints of the sides, diagonals, and etc. Instead of that, we are taking D4 itself as the D4 set. So what we are going to do here is D4 is a D4 set defined where the action is defined by D4 dash across D4 to D4. This is our G, and this is our X, and this is our X, defined by, take an element from here, and that goes to an element here that is actually GX G inverse. This is a conjugate, and that is how we are getting the conjugate classes. These classes are actually the orbits of D4. So we have this one here, and here we are going to fill this area. I'm not going to fill the whole area, but I'll show you how we are going to do this. So we are going to find conjugate classes for D4, meaning D4 is equal to C of D4 plus, if you have C number of one element orbit, then this will be C to R, then Ni. Or you can say GXI. So our first aim is to find the one element orbits of D4. Let us calculate this sigma 0. So this area, this portion will be, this will be filled up by sigma, this line, horizontal line is X and the vertical line is G. So G is equal to, here if you want to fill this cell, G is equal to sigma 0, X is equal to sigma 0. And if you compute this one, GX G inverse is equal to sigma 0, sigma 0, sigma 0 inverse, and that is equal to sigma 0, and that is here. We'll compute one more, sigma 3 here. So sigma 3 here, sigma 3 if you take here, G is equal to sigma 3, X is equal to sigma 0. So this portion will be sigma 3, sigma 0, sigma 3 inverse, which is again equal to sigma 3. So if you compute this, the whole column will be sigma zeros. So this is one orbit. That actually belongs to Z of D4. Another one, I'm going to get all the elements of ZD4 first. So another element is going to be in this area. Let us compute one of them. Let us take this. So this is in this area, in this column, what we'll have is G is equal to mu2 and X is equal to sigma 2. So this element will be mu2 sigma 2 mu2 inverse. And what is mu2 inverse? Mu2 inverse is mu2 itself. This is mu2 inverse. So this is actually mu2 sigma 2 mu2. So sigma 2 mu2. Sigma 2 mu2 is mu1. And mu2 to mu1 is sigma 2. So this is actually going to be sigma 2. So if you compute any element here, all of this will be sigma 2. So C of D4 contains actually sigma 0 and sigma 2. So we'll write this one as sigma 0 comma sigma 2. This is actually our D4. Actually the conjugate classes will be sigma 0 and sigma 2. These are the conjugate classes. One element class, we are going to find more. If you compute this column, we are going to get sigma 1 and sigma 3 in here. Similarly, here you get sigma 3 and sigma 1. So this orbit contains two elements. Like that, if you take this element here, you will get mu1 and mu2, and here you get mu2 mu1. Similarly, the other one will be delta 1 comma delta 2. So the conjugate classes of D4 are this. And the class equation will be, this will be again sigma 1 sigma 3 plus you will have order of this plus order of mu2 comma mu1 plus delta 1 comma delta 2. So the class equation is 8 is equal to 2 plus 2 plus 2 plus 2. This is the class equation. And these are the conjugate classes. Of D4. Our next problem is this. Every group of order 5 times 7 times 47 is abelian and cyclic. So by, or let us start with a group G. Let G be a group of order 5 times 7 times 47. So by first Sylow theorem, there exists unique first and third Sylow theorems, unique subgroups of order 5, 7 and 47. Let them be H, K and L. That is, order of H is equal to 5, order of K is equal to order of K is equal to 7, order of L is equal to 47. So see, the reason for existence of subgroups is coming from the first theorem. Uniqueness is coming from the third Sylow theorem. See, if you see, you can say G is equal to 47 times 35. This is our P and this is our M. Okay, and the Sylow's P group is of order 47 and there is only one, because the number of Sylow's P subgroup is 1 mod P and which should divide G. So that is the logic we are going to use here. Because these are unique Sylow's P groups, because H, K and L are Sylow's P subgroups, unique Sylow's P subgroups, they are normal in G, because conjugates are same, and that implies HK is a subgroup of order 35 in G. So there is only one subgroup of order 35. Okay? Because otherwise we'll have a different H and K, because otherwise H and K will not be unique. So HK is a subgroup of 35. And now HK here again, another reason for this being 35 is because H intersection K is equal to E. And we are going to use the earlier lemma. Order of HK is equal to order of H times order of K divided by order of H intersection K. This is 5, this is 7, and this is 1. And that is why we have 35 here. Another property of these subgroups are H intersection K is equal to E, K intersection L is equal to E, and L intersection H is equal to E. And that implies LK H or HKL. HKL is a group of order 5 times 7 times 47. This is or 35 times 47. This is actually 35. This is 47. And there is no intersection between these. So use the same lemma again. You get this. And that implies HKL is equal to G. This is a subgroup, this is a subgroup, and its product is G. And this implies G is isomorphic to HK times L. And HK is isomorphic to H, and that implies G is isomorphic to H cross K product of these three. These are all orders of subgroups of prime order. So order of H is equal to 5 implies H is actually isomorphic to C5 because it is a prime number. And K is equal to 7 implies K is isomorphic to C7. Similarly, L is isomorphic to C47. So that means G is isomorphic to Z5 times C7 times C47. G is then abelian definitely and is cyclic because 5, 7 and 47 are prime to each other. And that's what we want to prove. So before we end this session on Sylow's theorem, we'll do one more problem. And that is a group of order 96 cannot be simple. So before we come to the proof of this, one result we are going to use it from the earlier sessions. If H is a subgroup of G with index is equal to 2, then H is normal in. This is because the left cosets and right cosets are going to be identical. So let G be a group of order 96. So G is equal to 96 is equal to 2 to the power of 5 times 3. So the order of Sylow 2 group is 2 to the power of 5, and that is 32. So the number of subgroups of order 32 are congruent 1 mod 2 and should be divisible, should divide 96. So the possible number of subgroups of order 32 are just 1 and 3. Okay. If the number of subgroups of order 32 is 1, then that subgroup is normal and hence G is not simple, because there is a proper normal subgroup. Suppose G has 3 subgroups of order 32, say H and K. Okay. Now let us see what happens here. Using the previous lemma, H K is equal to H intersection H times K divided by H intersection K. So here H K is equal to HK divided by H intersection K. So this has to be less than 96, definitely, because it's a subgroup of, it's all elements are in G. And this is actually 32 times 32 divided by some number here. This number has to, when you compute this one, this has to be less than or equal to 96. So the order of H intersection K has to be 16. See, if you put 1, it has to divide 32 times 32. So it has to be 1, 2, 4, 8, 16, etc. If you put any other values, it will not be less than 96. And if you put 32, then HK is equal to H, which means H and K are same. So the only value of an H intersection K is 16. So H intersection K is a normal subgroup of H. H intersection K is a normal subgroup of H and K. Why? Because its index is 2. Because the index of H intersection K is equal to 2 is equal to K H intersection using this. So that is why this is normal in H intersection K. Now let us take a look at the normalizer of H intersection K. Normalizer of H intersection K. See, H intersection is already normal in H and H intersection is already normal in K. So the normalizer of H intersection K should be of order greater than 32 because each of this is 32. And should be a multiple of 32 and should divide 96 because it is already a subgroup, and that implies the order of the normalizer of H intersection K has to be 96, and that implies normalizer of H intersection K is equal to G, and that implies H intersection K is a normal subgroup of G, a proper normal subgroup of G, a proper normal subgroup. That implies G is not